So the existence and uniqueness theorem, like many other theorems, it can be written as an if-then statement. You've got an if part and a then part. And in any situation where the if part is true, you know the then part, the consequence, has to be true also. And for existence and uniqueness theorems, it's difficult to really see this in the way the problem is worded, but this is ultimately all about initial value problems of first order. So if we take a look at a first order initial value problem, first order initial value problem, what things do you need for an initial value problem?
Initial condition.
Yeah, you need an initial condition, and also, of course, the differential equation itself. So let's say you've got a differential equation like y prime equals some function of presumably t and y. Maybe you have, for example, y prime equals 3t minus 5y squared. In that case, the 3t minus 5y squared would be the f of t and y. And then to count as an initial value problem, you also need initial values. Let's say the point t equals t sub 0, y equals y sub 0. And usually the initial condition will be t equals 0, y equals something else, but it doesn't have to be t equals 0, just some constant t value, some constant y value. That's the one point we know the equation goes through. And ideally, we'd like to be able to say that this differential equation with that initial value has only one solution and has a solution at all. Because generally a differential equation, we can usually expect to have infinitely many solutions if it has any solutions at all. But the initial value should narrow it down to just one solution. The existence and uniqueness theorem is basically about what conditions have to be met in order to guarantee that. So the then part essentially says, then this initial value problem has one and only one solution. That is this initial value problem here. The if part is the conditions that have to be met in order to guarantee that. And it turns out those conditions are basically that this function has to be continuous. And it turns out that its partial derivative with respect to y also has to be continuous. If I remember correctly, f itself being continuous guarantees there's at least one solution. The partial derivative also being continuous guarantees that there's only one solution, that the solution is unique. It doesn't have to be continuous everywhere, they just have to be continuous on some region. Of the ty plane. So in general, they don't have to be continuous everywhere. We just have to be able to establish some region where they're continuous. As long as we can establish some region of space where those functions, the function and its derivative, are continuous, then within that region, we can guarantee there's one and only one solution of the initial value problem. Beyond that region, we can't guarantee anything. Maybe the function keeps going beyond that region and it's just fine. Maybe it doesn't exist outside that region. Maybe it does exist outside that region, but it becomes non-unique. Maybe it branches out into several possible trajectories. But within the region, we can guarantee there's only one solution and there is a solution at all. Oh, also, that region of the ty plane has to contain the initial condition in the first place. There may be several regions where they're continuous. What we care about is the region that contains the initial conditions. So this is the formal statement of the existence and uniqueness theorem. If this function and its partial derivative with respect to y are continuous on some region of the ty plane that contains the initial condition, then we can guarantee that this initial value problem has a solution and that that's the only solution that passes through that initial value. There will, of course, be infinitely many solutions to the differential equation, but exactly one of them passes through the initial value. So this should be true for any first order differential equation that satisfies this continuity requirement. Any questions on the meaning of that theorem so far?
It makes sense so far.
And let's do one quick example, just to see what sort of situations this might cover. Let's say our initial value problem is y prime times, let's say 2t minus 3y times y plus 5 equals t squared over t minus 4. Something like that. If this is our differential equation, then before we do anything with it, we want to rewrite it in this format. Y prime equals something about just t and y. Which means, of course, we'll have to isolate y prime by dividing both sides by these. So this would be our f of ty, this whole thing. And the first thing we want to check is, where is that continuous? Or to put it another way, is there any place where it wouldn't be continuous? Are there any ty values that would make discontinuities in this function?
So you would just set it equal to 0 and solve for any value that make it equal to 0 because it's in the bottom.
Yeah, anything that makes the denominator 0 would be a problem here. Because based on the functions involved, we've got t squared, you can square any value. We've got linear combinations of t and y. You can multiply any t or y value by scalars and add them or subtract them. But we have division by all this stuff. And you can't divide by 0. So we're going to have discontinuities at any t, y values that make the denominator 0. So what t values or what y values would make any of these factors 0?
4 for t.
Yeah, t cannot be 4. That would be a discontinuity. Anything else?
Negative 5 for y.
Yeah, y cannot be negative 5. And also, are there any t, y values that would make this middle factor 0, the 2t minus 3y?
T can't be 3 and y can't be 2.
Yeah,
at the same time.
We can't have t being 3 and y being 2 at the same time. In fact, we could extend that to a broader relationship. If we just want 2t, we want to make sure 2t minus 3y is not equal to 0. Can you isolate y there? Can we get some expression that y can't equal something?
2t over negative 3.
Yeah, or positive 3, I think, because we add 3y to both sides and then divide.
Oh, yeah, you're right.
So y can't equal 2/3 t. So it's not so much a restriction that y can't be a certain value or t can't be a certain value. It's an entire relationship between y and t that cannot happen. We cannot have a situation where the y value is 2/3 the t value. And that, if you graph that, ignore the inequality here. Suppose it was just y equals 2/3 t. What would that graph look like? If you were just graphing y equals 2/3 t.
That would just be like a linear line.
Yeah, we just have a line, specifically with 2/3 as the slope. So that line would provide essentially a boundary, a region that the solutions cannot be guaranteed to cross. So if we graph these discontinuities, if we plot them on a TY plane, we know T cannot be 4. That's going to be a forbidden vertical line. Y cannot be -5. That's going to be a forbidden horizontal line. And also Y cannot be 2/3 T. That's going to be a line through the origin that also cannot be crossed. So any of these red lines are borders that the function cannot cross, because those red lines form discontinuities in the original differential equation. Even if you were to solve this and find a function that could reach one of those lines or could cross one of those lines, we couldn't guarantee existence and uniqueness because it fails the original differential equation. So you want to check for T and Y values or relationships between T and Y that would make the original differential equation suffer from discontinuities. Those are the borders we're talking about between regions of continuity. But within any of these regions, like within this triangle, the differential equation is continuous. Or within this infinite region over here, or this infinite region over here, those would be regions of continuity. Any questions on that so far? And one other thing we should check, not only the function, but also its partial derivative with respect to y has to be continuous as well. So we also want to take the partial derivative of f with respect to y, essentially just treating t as a constant and differentiating as if y is the only variable, to see if that introduces any other discontinuities. And sometimes it does. There are some functions where when you take the partial derivative with respect to y, you find new discontinuities. But in a lot of cases, the discontinuities are going to be the same anyway. For example, this is a fraction. What sort of technique would you use to take the derivative of that fraction, that rational function? If you had to take the derivative of this function with respect to y, what technique would probably be foremost in that process?
Quotient.
Yeah, probably the quotient rule, which means you're going to take the derivative of the denominator times the numerator and the derivative of the numerator times the denominator. Are those individual derivatives going to introduce any new discontinuities?
I don't think so, because it's only partial for y. That doesn't.
Yeah, and even as we take those derivatives, like 2t minus 3y would just become 0 minus 3. T minus 4 would just turn into 0. Y plus 5 would just turn into 1 when you take the derivatives. And all we're doing is taking those linear functions and multiplying them by each other. That doesn't introduce any new forbidden y values or forbidden t values. And then the last thing you do in the quotient rule as well is divide by the original denominator squared. If you take this original denominator and square it, you still have all the same discontinuities. If we just had a squared on each one of these, t minus 4 squared in a denominator would still mean t can't be 4. Y plus 5 squared would still mean y can't be -5. So in this situation, and usually for situations where you just got ratios of linear functions anyway, ratios of, or in this case, polynomials, the partial derivative isn't going to introduce any new discontinuities. But for more complicated functions, sometimes it does. So it's important to check. In this case, though, it looks like these are the only discontinuities. So these red lines are the only forbidden zones. And that slices the plane up into, looks like 1, 2, 3, 4, 5, 6, 7 different regions. So there's 7 regions of continuity, 7 regions where we can guarantee that there exists a unique solution. How would we choose which one of those we would actually be talking about? Or what other information would we need?
The initial condition.
Yeah, we'd also need the initial condition. So let's say the initial condition was given. Let's say the initial condition was t naught equals 0, y naught equals -1. That would be right here on the graph. And that suggests that the region we're talking about is this region here. So this triangular region would be the only region where we could guarantee there is a solution and only one solution. That solution might leave the region, we don't know. All this says is about where we can guarantee there's a solution and only one solution in this region. It doesn't say anything about what might or might not be happening outside of that region. Or alternatively, if the initial condition was, let's say the initial condition was like 0 for t and +1 for y, that would be up here. So that means the region where we could guarantee continuity would be this infinite region. So that region would be where we could guarantee there exists a solution and only one solution. Or alternatively, what if it was something like t equals 0, y equals -5? In that case, what would we say? What could we conclude?
The region at the bottom. Yes.
If we look at -5 exactly though, what's important about y equals -5 here?
It hits the forbidden line.
Yeah, that's on the forbidden zone, this line of discontinuity. So if the initial condition is on one of those discontinuous points, if the initial condition makes the discontinuity in the original differential equation, then we just can't guarantee anything. Maybe there's a solution, maybe not, but it's not in one of the regions where we can guarantee there's a solution. So we can't really conclude anything. So that's really the important things to look for, I would say. Take a look at the original differential equation written in the form of y prime equals some function of t and y. Check that function of t and y and its partial derivative with respect to y to see if there are any discontinuities, any t values, any y values, or any relationships between t and y that make the differential equation discontinuous. That allows you to carve up the ty plane or xy plane or whatever variables you're using into regions of continuity. And whatever one of those regions the initial value is in, that's the region where you can guarantee there's a unique solution. Or if the initial value is on one of the discontinuity regions or one of the lines of or curves of discontinuity, that means you can't guarantee anything. So it's a very abstract theoretical concept. I think that it's much less in the realm of practical application than some of the other stuff from differential equations. But from a theoretical standpoint, it's very important to be able to know, yes, this differential equation does have a solution before we spend time trying to find that solution. Any other questions on that so far? And one other thing on this theorem, like many situations in differential equations, this becomes much simpler and much easier to deal with if the differential equation happens to be linear. If we're talking about a linear differential equation, any linear first order equation can be written as y prime equals, or let's say y prime, let's go ahead and just write it as y prime equals something of about t times y plus something about t. That would be linear, right? We just got y prime equals something about t times y plus something about t. Usually we write the p of t times y on the other side of the equation, but we could just subtract it from both sides anyway. If you've got a differential equation like this, then this would be our f of t and y. Are there any y values that make this discontinuous? That is there any value you could plug in for y here that would cause problems?
I don't see any.
Yeah, it looks like y is fine no matter what it is. You can take any number you want and multiply by p of t and add g of t to it. So this has no y values that make problems. Every y value is permissible. The only problems that could possibly show up are maybe some t values if it makes p of t discontinuous or if it makes g of t discontinuous. So there might be t values that make p or g discontinuous. So we have to be concerned about t values, but every y value is okay. Y can be any real number. Which means for linear differential equations, if it's of the form y prime equals something y plus something, in that case, we don't need to worry about drawing out curves or lines of discontinuities. All we have to care about is specific t values that cause discontinuities. And then when we take the partial derivative, we just get p of t plus nothing. So that doesn't introduce any new discontinuities. So that's one of the advantages of working with linear differential equations. You only have to care about discontinuities from t values, not complicated shapes that are regions of discontinuities. For example, if we're talking about, let's say y prime equals square root of t minus 3 times y plus 1 over t plus 1. In that case, are there any t values that would make this discontinuous?
Anything that's greater than 3?
Yeah, t has to be greater than 3. Or could be equal to 3, because you could have square root of 0, that's fine. And also, does this have any t values that make it not work?
No, -1 for t.
Yeah. And yeah, that's already kind of excluded by t having to be greater than 3. So in a case like this, as long as it's linear, you just need to look at t values that make either of these functions discontinuous. And then you don't even need to make a whole two-dimensional graph. You can make a number line, just the t-axis alone. Mark any discontinuities on it. And we can say that 3 is fine. Anything greater than 3 is fine. Anything less than 3 doesn't work at all. So this is a region of discontinuity. But we can say that as long as the initial condition involves t being 3 or more, we can guarantee, yes, there is a solution and only one solution on the interval from 3 to infinity. So we say the interval would be interval of existence of the solution would be from 3 to infinity, in this case, including 3, because 3 is allowed in this situation. You can have square root of 0. Any questions on that? All right, then let's take a look at that example problem that you sent me with the separable equation. Let me write that on the board here. Looks like we have y prime, which I'm just going to convert directly to dy dx because that's going to be more useful, equals 6x over y plus x squared times y. And there's an initial condition as well, but we can get to that later. What we want to do is solve this differential equation, presumably by separation of variables. And how would we accomplish that? How could we split up the x's and y's here? Is there any way we could rewrite this as a function of just x and a function of just y combined with multiplication and or division?
You can do y multiplied by 1 plus x squared at the bottom.
Yeah, since both of these terms have y in it, we can factor out y and get 6x over y times 1 plus x squared. So this now seems much more like something about just y and something about just x. That is the function of y, which in this case is just y, and the function of just x, combined with multiplication and division only. That's really the key to differential equation or the separable differential equations. There's a lot of ways to write it in very formal mathematical terms, but I just think of it as you've got to have a function of just y and a function of just x combined with multiplication and or division only. As long as you can write it in that format, function of just y, function of just x combined with multiplication or division, then that's separable. And in this context, how would you separate the variables here? How would you get all the y's to one side and all the x's to the other side?
Just cross multiply them.
Can you be more specific? Because we're not getting rid of the whole denominator.
Oh,
What are we multiplying both sides by?
multiply both sides by y and dx.
Yeah, if we multiply both sides by y, then the y and in the numerator and the y in the denominator cancel out. And we can also multiply both sides by dx. Formally, we're integrating both sides with respect to x, but on the left side, they essentially cancel out due to the chain rule. But we end up with y dy equals 6x over 1 plus x squared dx. And at this stage, now that we have separated the variables to just y's and dy's on one side, just x's and dx's on the other side, what can we now do?
Integrate.
Yeah, at this point, we can actually attach an integral sign to both sides and say that we are integrating the left side with respect to y and integrating the right side with respect to x because of the dy and the dx that are already there. Integral of y dy would be what?
Y squared divided by 2.
Good. And then on the left side or the right side, this does not look like an easy, obvious antiderivative. But what technique do you think might work here in order to evaluate that integral?
Use substitution.
Yeah, the fact that we've got this nice, neat function within a function, specifically that 1 plus x squared in the denominator, anytime we got a function within a function like that, it often suggests that use substitution is at least worth looking into. And the most important thing is the derivative of that function within a function. What is the derivative of 1 plus x squared?
2x.
Right, and we have a scalar times x in the numerator as well. That's really the important thing you want to look for. A function within a function whose derivative appears somewhere else in the integral as well. And formally, we would write this out as let u equal 1 plus x squared, at which point the derivative du dx would be 2x. We could then multiply both sides by 2x, or sorry, by dx. And one thing you could do here is you could say anywhere you see 2x dx, you can replace that with du. We have 6x dx, but how could you rewrite 6x dx?
Three du.
Yeah, because 6x is the same as 3 times 2x. If we split that up, we could say 2x dx is du. Or alternatively, if there's not an obvious way to split it up like that, if you can't see an easy way to fill this in somewhere, you could continue isolating dx, divide both sides by 2x, and you get dx equals du over 2x. So one way you could proceed here is just replace dx with du over 2x, and then the x's cancel out, and the 6 over 2 reduces to 3 anyway. Either way, we end up with 3 du. So that looks like integral of 3 du over, and then 1 plus x squared is just u itself. Any questions on that integration by, or that use substitution so far? And then that 3 is a constant, so we can pull it out, and what's left?
1 over u du.
Yeah, and integral of 1 over u is going to be,
Log of u.
yeah. So the 3 we pull out as a constant multiplier. 1 over u becomes natural logarithm of u And also, since we're looking for all possible solutions, we should include a plus a constant here. At this point, we also may as well fill in the value for u, because u represented 1 plus x squared in the first place, just a placeholder for that. So let's fill that in. And what else would we still need to do to isolate y and get an explicit solution?
Multiply by 2 and square root the right side.
Right. Multiplying by 2 turns a 3 into a 6. I guess we don't really need the absolute value because 1 plus x squared is always positive anyway. And 2 times c is just another constant, so we can just write it as another plus c. Then take the square root. Also, again, since we're looking for all possible solutions, what else should we include as well as the square root?
Plus or minus.
Yeah, anytime you're taking square root of both sides, at least consider the idea that it could be plus or minus. And that should be our general solution. Any questions on that so far? And then to find the specific solution, since it gave us an initial value, you could just plug in the x value that's provided and the y value that's provided, solve for c. And also, based on whether y is negative, that initial value tells you whether you should write this as plus or as minus. Because the general solution includes plus or minus, but any specific solution will just have one or the other. And you choose which one, in this case, based on which one actually gives you the correct y value. Like I think in this case, the y value was -7, so you need to use negative here to make that work. Any other questions on that? And since we've got a little bit of time left, let's also take a brief look into the idea of autonomous equations. That's another category of first order equations that's very specifically defined in a way that narrows it down to equations that are very easy to solve by certain methods. Specifically, an autonomous differential equation and in this case, I'm going to use t as the independent variable because we're usually talking about time here. Let's say y is some function of time. An autonomous differential equation would be a differential equation where derivative of y with respect to t equals something about just y. And in particular, doesn't depend on t at all. So for instance, y prime equals 3y. This would be autonomous because it's telling you how y prime, the rate of change, is related to the value of y itself with no time dependency. Most of the container problems you've been seeing, where you've got like salt pouring into a container, the mixture draining out, those are usually autonomous because nothing is really happening as time passes. We're changing how much fluid, how much salt is in the tank, of course, but we're not changing how quickly we're pouring salt in. So for example, if you had like ds dt equals, maybe your rate in is 50 grams of salt per minute and your rate out is like 3s over 1,000 or something. You see differential equations like this all the time when dealing with container problems. The important thing is this doesn't depend on t. It only depends on how much salt is in the container right now. So autonomous equations are also often called time independent or history independent. It doesn't matter what time it is. It doesn't matter what has happened so far. All you need to know is what's the value right now, and you can calculate how fast the value is changing right now. That's all an autonomous differential equation is. It's describing the relationship between how much there is right now and how fast it's changing right now. Any questions on that definition so far? And one of the results of this, if you just have derivative of y with respect to t equals a function about only y, what's one way you could always solve a differential equation of that format?
Separable?
Yeah, any autonomous equation is automatically guaranteed to be separable. Because if you think of this as just like f of y times 1, you could think of the 1 as a constant function of t. divide by f of y, multiply by dt, and you can integrate both sides. So any autonomous equation is guaranteed to be separable. That's not always going to be an easy way to solve it though, because 1 over f of y, there's no guarantee that this is easy to integrate or even possible to integrate. You can always at least write the solution in the form of an integral, but that integral might be very inconvenient to deal with. But even if this is not something you can easily integrate, there are other techniques you can use to analyze the behavior of the autonomous differential equation without even solving it. Starting with the idea of a direction field again. For example, let's say we take a look at the simple one, dy dt equals, let's say, 3 times y. No dependency on t, this just says the rate of change in y is 3 times as much as the value of y. If we were to make a direction field of that, let's say we plug in 0 for y and 0 for t. We're going to get 0 as the result. 3 times 0 is 0. So at the origin, we have slope 0. Or let's say we go up to y equals 1, t equals 0. Plug in 1 for y, 3 times 1 is 3. So you have slope 3. Go up one more space, 3 times 2 would be 6. So the slope would be 6. Or if we go down, if we plug in -1 for y, 3 times -1 would be -3. So we'd have a slope of -3. Down one more space, 3 times -2 would be -6. So we have a slope of -6. As I'm doing this, as I'm calculating these slopes, what value am I not using? What do I not need to know?
T.
Yeah, I don't need to know the t value because that doesn't show up in an autonomous differential equation. And if t doesn't matter at all, that means if I use a different t value, like let's say I take this point and move to the right one space, what happens to the slope?
It remains the same.
Yeah, it remains the same. If y is 1, then the slope is going to be 3 regardless of what t is. So I really only need to make one column of the slope field, and then I can just copy that and paste it to any t value. Every column of the direction field is going to look identical. So it's very easy to make the direction field for an autonomous differential equation. You just make one column in detail, and then copy, paste, 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 and you've got your direction field, which makes it much easier to draw out sample solutions. So even without solving this, it looks like these are, what sort of function does this look like?
Exponential.
Yeah, we can get the idea that this is probably an exponential function. And in fact, the derivative of an exponential function is a multiplier times the original exponential function. So this fits together. Also, instead of drawing out the entire direction field, like I said, we only have to care about one column. So often, instead of drawing out the entire direction field, we just draw one column, which is usually called the phase line. A phase line is essentially just one stylized column of the direction field. And usually what we most care about is the equilibrium solutions. Specifically, any y value that leads to the derivative being 0. Are there any y values that lead to the derivative being 0 here?
0.
Yeah, so if y is 0, then we get 0 slope. That's an equilibrium solution in the sense that if you start at 0, you'll just stay at 0 forever. What if you're above 0? If y is greater than 0, what does that tell you about the slope?
It'll be positive.
Right. Which means we can fill this in with, usually we just draw an upwards arrow. This up arrow signifies any y value above 0, above that equilibrium, is going to get pushed further upwards, a positive slope. Or if you're below 0, if y is negative, then the slope will be
Negative.
negative. So we'll draw a downwards arrow. This diagram just represents if you're at y equals this value, you'll stay there forever. If you're above that value, you get pushed further up. If you're below that value, you get pushed further down. So what kind of equilibrium would we call this? Would this be stable or unstable or semi-stable?
It's unstable.
Yeah, this is unstable equilibrium. Equilibrium in the sense that if you start at 0, you'll stay at 0 forever, but unstable in the sense that if you start a little bit away from 0, you'll get pushed further away. As opposed to stable would mean if you start away from the value, you get pushed back towards it. So this phase line, a simplified direction field that only shows one column and stylizes the slope field with slope arrows with just single up or down arrows, is a very useful way of identifying and analyzing the equilibrium solutions and figuring out as time goes to infinity, what's the behavior. Looks like in this case, everything's going to diverge either to positive or negative infinity, except for the one solution that stays 0 forever. Any questions on that phase line analysis so far? Well, let's take a look at a slightly more complicated one. Let's say we have y prime equals, let's say, y times y minus 4 squared times y minus 10. And this might originally be a multiplied out format, but if it's not, if it is, you want to factor it first. Having it in factored form is very useful, because if we want to know where are the equilibrium values, equilibrium just means a y value that results in the derivative being 0. Are there any y values that result in the derivative being 0?
So that would be y equals 0, 4, and 10.
Yeah. Y equals 0, y equals 4, and y equals 10 would all lead to the result being 0 slope. So what we can do then is we can draw out a phase line and mark the important points: y equals 0, y equals 4, y equals 10. And this doesn't have to be to scale, really. You just need to mark and label the important points: 0, 4, and 10. If it starts at any of those values, it'll stay there forever. But we want to consider what's going on in between those as well. For example, if we take a look at each one of these factors, what do you know about the value of y minus 4 squared? What's that always going to be?
It's positive.
Yeah, the squared means this is always positive. Let's say, though, we're talking about a value less than 0. If the value is less than 0, then y, of course, is negative. Y minus 10 will also be negative. Negative times positive times negative is going to be
negative.
We're multiplying a negative times a negative, though. So
Positive.
yeah, which means anywhere below 0, we're going to get a positive slope. That is an increasing function. So anytime the y value starts off below 0, the graph is going to be an increasing function, presumably increasing and approaching 0 as an asymptote. What if we're between 0 and 4? So we're above 0, this is positive, but we're still below 10. So a small number of minus 10 is still going to be negative. What do you get if you multiply those together?
That's negative.
So we're going to get a decreasing function in that region between 0 and 4. And then if we go above 4, y is still positive, but a number above 4 but below 10, minus 10, is still going to be negative. So this region will still be a decreasing function. But what if we go above 10? If we have a really big number we're plugging in for y, what do we get?
Positive.
Yeah, because a number larger than 10, minus 10, will now become positive. Now, all these terms are positive, so that will be an increasing function. So this would be the complete phase line. It's describing, it's showing all of the labeled equilibrium values, and it's showing in between or beyond those regions in these zones is the function an increasing function or decreasing function. And we can use that to now label all of these equilibrium points. For instance, at 10, would you call this stable or unstable or what?
It's unstable.
Yeah, much like 0 in this one, everything nearby in this neighborhood is diverging away from that point. So this would be unstable equilibrium. And at 0?
That would be stable.
Yeah, everything's nearby is approaching towards it. So that would be stable. And what about at this point here?
That's semi-stable.
Yeah, this would be called semi-stable or sometimes called half stable, because the stuff above it is approaching it, the stuff below it is going away from it. So it looks stable from one side, but unstable from the other side. So what this would look like on a graph, we know we've got equilibrium at 0, at 4, and at 10. We know that everything below 0 is approaching it upwards from below, presumably starting off with a very weak slope nearby and stronger slope further down. Between 0 and 4, we've got a downward slope, presumably a weak slope near equilibrium and a steeper slope in between. Between 4 and 10, we also have downward slope. And then above 10, we've got an upward slope, positive slope. So once you've drawn the phase line, it's very easy to turn that into a direction field, starting with the equilibrium values and then proceeding from there. And at that point, you can draw some of these sample solutions. Every equilibrium will be just a horizontal line, of course. The other ones, for instance, might be, this looks kind of like exponential growth. This looks like exponential decay. These ones, though, start off shallow, then get steep, then flatten out again. So that looks like what's usually called a logistic growth curve, or I guess in this case, a logistic decay curve. Starts off not very steep near asymptote, then gets steeper and steeper in between, then levels off to another asymptote. But this is the sort of solution we get from this differential equation using the phase line to analyze it. And often this is all we care about. Even without solving this and finding an explicit solution or any analytical solution at all, the phase line and or direction field gives us information about what the curves look like and what, most importantly, what's happening to them after a long time. And in many situations, that's the only thing we need to know anyway. Any other questions on the autonomous differential equations? All right, then I will see you next time.
Thank you.
You're welcome.